Hello friends, Eli Hibbett here with the Pwn Your Homework Physics Series podcast. If you're looking to prepare, review, or gain an added edge or point of view about topics in physics, then look no further. Tune in each week to unlock your understanding of the physical world surrounding us. And now let's dive right in.
Hey, how is everybody feeling today? I am your host, Eli Hibbett, back at you again with another episode of the Pwn Your Homework Physics Series podcast. And this week's edition is episode number 73, Dot and Cross Products Examples, Part 1. So we're going to be diving into a little example action. Last couple of episodes have been concentrated mostly on step-by-steps of doing dot and cross product, kind of understanding what the whole thing means. Went through a little right-hand rule, but now we're going to get our hands dirty a little bit and go through some examples. But first, let's take a look up in the sky. Cloudy day here on Long Island, New York. Not sure if it'll clear up by tonight, but we are in full moon mode, 100% illumination. And since it's the month of October, the full moon is referred to as the hunter's moon. Because, as autumn is approaching, everybody's getting ready. It's deer season. And getting ready for winter, the long, cold months ahead. So, hunter's moon, here we go. The harvest is over. So that's what's going on up in the sky. A little update from our friend at the physics quiz. There is an updated version with new questions. Most of them, I guess, are on the easy setting, but new questions galore. So do go on over and check that out. His Twitter handle is at the physics quiz, and a lot of cool questions. I finally scored my first 10 out of 10 on easy. I was very proud of myself. I posted it on Twitter on our Pwn Physics Twitter feed, PWN Physics, where lots of cool stuff happening over there. But yeah, I finally did wind up getting the perfect score. I was really jazzed about that. I was going through with some friends this weekend, and we collectively took the quiz and got a perfect score. So if you're interested in that particle physics stuff, do check it out. Again, the physics quiz for iPhone apps for sure. And so a little update from the one of the friends of the Pwn Physics universe. So that's what we're doing over there. And without further ado, let's dig into a dot product example. So with cross products, I think we'll just cross two vectors first and then kind of see where that takes us. But with dot products, you're just sort of given a single number at the end. So I think we can actually do kind of an applied example here. So I have a question for you. A strapping young man exerted a force of, this vector is in 3 dimensions, 10 newtons, 10 newtons, 10 newtons, moving a box from position 1, 2, 3 to position 4, 5, 6 on a 3D Cartesian axis, where all positions are defined in meters. What is the total work done? So, we need a little bit of we're doing an applied example here, guys. This is really cool. So we need to know a couple of equations that actually relate physical quantities, and then we'll be able to calculate that no problem. So the first thing we need to know is that work, which is a scalar quantity, is equal to F dot D, where force is the F, and the displacement vector is D. So we have two vectors, F and D, and if you dot them together, it gives you the work done. So that's great. So we already have our force vector, 10 newtons, 10 newtons, 10 newtons. Nice and easy. But how are we going to calculate our displacement from what was given to us in the problem? Well, we know that the box moves from position 1, 2, 3 to position 4, 5, 6. So we need another little relationship. And that relationship is that displacement is equal to your final position minus your initial position. So we know the initial and final positions. So we have to do a little sub work here and calculate our displacement first. So we have 4, 5, 6 minus 1, 2, 3. So what you do when you subtract vectors, which we've already went through, is that you subtract the values in each axis. X minus x, y minus y, and z minus z. So we have 4 minus 1, 5 minus 2, and 6 minus 3 in the x, y, z directions respectively, which gives us a displacement vector of 3, 3, 3. Notice in the vector subtraction that each component of the position was subtracted individually, and that all three directions combined together give us our final displacement vector. So now we have everything we need. We got our 3, 3, 3 displacement vector and our 10, 10, 10 force vector. So now we're going to dot them together. So I think that we're actually pretty deep into the step-by-steps here. So we identified the two vectors, force and displacement. Identified the number of dimensions. Well, we have 10, 10, 10 and 3, 3, 3, so that's 3 dimensions in each vector. We're going to multiply like components from each dimension together. So now we're in this step. So we take our 10 newtons times 3 meters plus 10 newtons times 3 meters plus 10 newtons times 3 meters. So we have 30 joules in each direction. Now we're going to add all like component multiples together. So here we have 30 joules. This is very easy in this example. 30 joules plus 30 joules plus 30 joules, giving us our final answer of 90 joules. So that is the work done. So you could actually, just knowing how to do a dot product, calculate work if they give you kind of a softball style force and displacement vector. You can do that calculation and do a physics problem right now. Easy. No sweat whatsoever. We did it. Walked through the steps in about, I don't know, how long was it? A couple of minutes, and we're done. So that's a dot product example. We did it kind of algebraically. We did it with values. We did a little subcalculation with displacement, and we got our answer. And that's really all there is to it. If you walk through the steps and you know a little bit about physics, it's not so bad, guys. So there we go. Dot product example done. So now let's move forward and go into our cross product question. All right, so here we go. For the following vectors, vector C is equal to 2 comma 5, and vector D is equal to minus 4 comma 9. We have two calculations to do here. The question asks us to calculate C cross D and to calculate D cross C, and then asks what are the differences and what are the similarities. So alright, let's dig into our step-by-step on how to do cross products in 2 dimensions. Identify 2 vectors in your coordinate system as AX, AY, and BX, BY. So in this problem, we're going to kind of liken vector C to vector A and vector D to vector B. So in the step-by-step, we have AX and BY. So anytime we have something to do with A, we'll be replacing with our C vector, and D will be replacing, or anything to do with vector B, we'll be replacing with our D vector. So let's just take a second here and write everything out. So AX is going to be equal to 2, AY is going to be equal to 5, BX is going to be equal to minus 4, and BY is going to be equal to 9. And now that you've set this up, you can just go through the steps of how to do a cross product in 2 dimensions straight up, and we can just calculate it. So now let's move on to step 2. Multiply AX and BY. Now we can easily reference step 1. Now that we've sort of laid out what AX, AY, BX, and BY are, and just do multiplication. So AX times BY is 2 times 9, which is 18. Step number 3, multiply AY and BX. Again, 5 times minus 4, which is minus 20. Now step number 4, subtract step 2 from step 3. So we have 18 minus negative 20, which is equal to 38. And then we slap a K hat at the end and box our answer because we're done. So we have, the vector is 38 times K hat. And if you wanted to write that as, a 3D vector, you would put it in brackets. 0, 0, 38 is what C cross D is equal to. So 38 in the positive Z direction, with a C being vector 2, 5, and D being vector minus 4, 9. So now, let's calculate it in reverse. D cross C. What do you think the difference is going to be? Well, we're going to have some different values in our AX, AY, BX, and BY slots, but Will that change what happens algebraically? Well, there's only one way to find out. All right, so step number 1, identify our two vectors in coordinate system as ax and ay and bx, by. So here, our components ax and ay are going to come from vector d, and our components bx and by are going to come from vector c, since we're kind of doing it in reverse. So now we have ax is minus 4, ay is equal to 9, bx is equal to 2, and by is equal to 5. So now that we've done that mapping, which is kind of critical in this step 1, we can just go through steps 2, 3, 4, and 5 and just perform multiplication. So multiply ax and by. It's going to be minus 4 times 5 is equal to minus 20. Step number 3, multiply ay and bx. So that's going to be 9 times 2, which is equal to 18. Okay. Now, subtract step number 2 from step number 3. So we take minus 20 minus 18, which is equal to minus 38, and place a k-hat as step 5, and box your answer, you're done. So d cross c is equal to brackets 0, 0, minus 38, close bracket, or alternatively, minus 38 times k-hat. So the difference is, well, what are the similarities? The similarities is that the magnitude is the same. It's 38 k-hat or minus 38 k-hat. So the 38 is the same. And what is different? Well, the vectors are pointing in opposite directions. We have one pointing in the positive z-axis, c cross d, and d cross c at minus 38 k-hat is pointing in the negative z direction. So we have a couple things we can draw from this. The magnitude is similar, and the vector in 2 dimensions, is directed entirely in the z direction. That's pretty much what's similar. And what is different is the direction of the vector. So c cross d is equal to minus d cross c. I think that's what we're able to draw. And this is actually true. I'm not just, kind of just taking a look and seeing what it is. C cross d is equal to minus d cross c. That's sort of what you can glean from this. And if you take 2D vectors and cross them, what you get is that they're pointed in different directions along the z-axis. And that sort of changes in 3D. It becomes a little more general because you have 3 dimensions, and so the magnitude is the same, and then the direction is swapped as minus 1. So I think we're going to kind of leave it there for now, and next we're going to prove this. We're going to prove it kind of as a theorem, and we're going to take generalized vectors vx, vy, and wx, wy, and calculate v cross w and w cross v, and see if we can actually get it to algebraically fall out. But now that we're sort of going back and looking at those step-by-steps, do you see how the determinant comes in there? I mean, you're pretty much just like, okay, if you have a vector in 2 dimensions, calculate the determinant of the matrix and put the k-hat on there. And that's exactly what you do as one step of a 3D cross product, right? Pretty cool, huh? And we picked up a very, 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 very useful piece of information, which is that if you take vectors c and d, c cross d is equal to minus d cross c. That's incredibly useful because if you're doing algebra and you have 2 vectors and you wind up, there's something nice that you could do if only it was reversed. You can reverse it, add a minus sign, and keep on going. I know that probably doesn't seem very valuable to you at this point, but let me tell you, as you get up higher on into more theoretical style physics, that is a great tool to use, especially in E&M. You're going to use it all the time, and so a couple of very important things coming to the maybe unsuspecting listener, so keep that in the back of your head. So we did a couple of cool examples. We actually did an applied physics example. Dot product of work is equal to F dot D. And actually calculated a physical quantity, 90 joules of work. If you take a vector 10, 10, 10 newtons and move something from your Cartesian coordinate system 1, 2, 3 to 4, 5, 6. Couple of easy answers, in terms of how the math falls out, but we're just dipping our toe in the water here and getting used to how it all works. So I think it's very useful. We're going to be rocking through dot and cross product examples, a couple more parts at least, I think. We got to do the algebra to understand this proof of how it works. Do cross product in 3 dimensions, maybe even a dot product in 3 dimensions, and then we'll do a little bit of applied action. I think we'll do a real cross product example. And so that's where we've come, and that's where we're going. Again, check out the physics quiz on Twitter and pick up the app. You know, I love it. I just like the app. And so I thought that, if you're listening to this podcast, it's definitely up your alley. So at least, scope it out. But I think that's going to do it. Halloween coming up, and a harvest moon, or hunter's moon even, in the sky. So, yeah, that's what's going on in our world. Cross products, dot products, vectors, hunter's moons, and physics quizzes. So I hope you're doing well. I hope you're jamming through your course load, and that you're tuning into the podcast and getting a little bit of enjoyment out of it. So wherever you are, thanks for listening, and stay frosty, stay in the zone, and I'll catch you next time, guys. Take care.